today's session, I will be discussing about the shear force and bending moment diagrams for overhanging beams subjected to concentrated loads and uniformly distributed loads. Beams overhanging on one side and both sides. Coming to the convention, it was already discussed in the previous sessions. For shear force, left side upwards and right side downwards positive, and vice versa. Similarly for bending moment, hogging bending moment negative and sagging bending moment is positive. Let us directly discuss the examples. So, to draw the shear force and bending moment diagrams for the overhanging beam as shown in the figure. So, except for cantilever beam, in determinate beams, we have to find the reactions first in simply supported or overhanging beams in order to draw the shear force or bending moment diagrams. That means to find the shear force or bending moment at any section, the reactions also need to be known, because they also contribute to the shear force. We will find out the shear forces only after finding the reactions. Okay. And for finding reactions, we apply the condition sigma ma equal to 0 or sigma mb equal to 0. We will take the moments about the support points A or B so that one of the unknowns is eliminated. Taking moments about A, we will have the moment due to RB anti-clockwise, which is RB into 5, and that is equal to the clockwise moments, sum of clockwise moments, 30 into 1 plus 40 into 6.5 plus 20 into 3 into 3.5. This is total load, W into L. So intensity multiplied by the length of UDL gives total load of UDL multiplied by the distance from the center to the point A. This is 3.5. Okay, distance at which the resultant of UDL acts, that is 3.5. So from this you will get RB as this is 210 and 30, 240 plus 260. That is 500 by 5. That is 100 kilonewtons. Okay. Therefore, RA is equal to total downward load 30 plus 40 plus 20 into 3 minus RB. Okay. Because RA plus RB is equal to total downward load. So RA is obtained as 30 from this, 30 kilonewtons. Okay. Yeah. So once you find the reactions, we can find the shear forces at various sections. How many sections we consider here? We have to consider sections for every change of loading. We need to consider one additional section here. Okay. So between A and E, we consider one section. E and C, one section. C and B, one section. B and D, one section. Okay. And for the sections between AE and EC, we take origin from A, and for the other two sections, we will take origin from B. That is for our convenience. Okay. So now, for section between AE, let us go to the next page. For section between AE, X varies from 0 to 1. So shear force at section X is RA. Okay, only one force reaction acting RA, that is 30, and it is positive 30 kilonewtons, positive as per our convention. Okay, and it is independent of distance x. You can observe that. Okay, so shear force will be same at both the ends A and E. Okay, that is 30 kilonewtons positive. Okay, and coming to bending moment. Uh, Bending moment at section x is RA into x, that is 30 into x. It is also positive because sagging moment. It is sagging moment. And it depends on x. You can observe that. So bending moment at A, that is at x equal to 0, is 0. And at x equal to 1, bending moment at E is 30 kilonewton meters. Okay. And next, between points E and C, consider the section, and origin is from A again. So the limits for x are from 1 to 2. The limits for x are from 1 to 2. So x varies from 1 to 2. So coming to the shear force, 30 RA minus 30. Okay. Yeah, RA is 30, which is positive, left side upwards, minus 30. This is left side downwards, so it is negative. So 30 minus 30 is 0. That means shear force at E and shear force at C is 0. That means between E and C, the shear force is 0. And coming to bending moment, we have 30 into x, that is RA into x, minus 30 into x minus 1. 30 into x minus 1. And at x equal to 1, bending moment at E is equal to, this term is 0, so you will have 30 kilonewton meters. And at x equal to 2, bending moment at C is 30 into 2 minus 30 into 2 minus 1. So it is 90 kilonewton, 60 minus 30, 30 kilonewton meters. Okay, it is clear. So bending moment also remains constant between E and C for this case. Okay, coming to the portion BD, x varies from, for this section, x varies from 0 to 1.5, 0 to 1.5, and shear force at x is equal to, 40 kilonewton. It is positive because our convention is right side downwards is positive. Okay, and this is independent of position of section, so it remains constant between D and B. So shear force at B is 40 positive. Okay, and bending moment at x is negative because it is a hogging moment, 40 into x. Okay, bending moment at x is 40x with negative sign as it is hogging. So at x equal to 0, bending moment at D is 0, and at x equal to 1.5, bending moment at E is minus 60 kilonewton meters. Okay, next considering portion CB, okay, shear force at X in portion CB, shear force at X is from this figure you can see 40 plus right side downwards positive, so 40 plus 20 into X minus 1.5. These two are positive, minus RB, because RB is upwards on the right side, so it is negative. So the shear force at X is 40 plus 20 into X minus 1.5 minus RB 100. Okay. So this becomes 20 into X minus 1.5 minus 60. So this is also dependent on X now. At X equal to between we are considering portion EC, isn't it? No, CB. Portion CB you are considering. So the limits for X will be, what are the limits for X here? X equal to 1.5 to 4.5 meters. Okay. So at X equal to 1.5, section will be at B. So shear force at B is, this term is 0 and it is minus 60. Okay. And at X equal to 4.5, shear force at C. Shear force at C. Sorry. Shear force at C is, substituting 4.5 for X. So 20 into 3 and minus 60. So 20 into 3 is 60 minus 60. So it becomes 0. Shear force at C is 0. Okay. Coming to bending moment at X. Coming to bending moment at X. So what are the forces acting now? Bending moment at X is RB into X minus 1.5, that is positive sagging bending moment, minus 40 into X, minus 20 into X minus 1.5 into X minus 1.5 by 2. Okay. So RB 100 into X minus 1.5 minus 40 into X minus 20 into X minus 1.5 square by 2. Okay. Yeah, these two are hogging bending moments and this is sagging bending moment. Okay. So now substituting the limits, X equal to 1.5, you will get bending moment at B. So at X equal to 1.5, this term becomes 0 and this term becomes 0, first and third terms. So 40 into 1.5, you will get 60 kilonewton meters, minus 60. And at X equal to 4.5, you will get bending moment at C. So 100 into 4.5 minus 1.5. Okay, that is 3. And 40 into 4.5 minus 10 into, because 10 into 3 square. Okay. So this is 40 into 4.5 is 180 and 90. So 270. 300 minus 270, that is 30 kilonewton meters. Okay. And this varies parabolically here. Between BC, the bending moment varies parabolically. And at the same time, the shear force changes sign between BC. So by equating the shear force to 0, this value to 0, you will get x where the shear force changes sign. Okay, that is 60 by 23 plus 1.5, so 4.5. At 4.5 x value, the shear force changes sign. Okay, yes. Now we can draw the bending moment and shear force diagrams for this. Okay, coming to the shear force diagram, we have A, D, B, C, and E. First locate the points. And the shear force at A is 30. Okay, it is positive. Shear force at A and E is 30. Okay, shear force at A and E is 30. And the shear force at C at E is 0. Okay, and coming to this BD, shear force at D is 40, and which remains constant here. It is 30, and from 40 the shear force changes, varies linearly here. You can see what is the shear force at B, minus 60. At B it is minus 60 because there is a reaction of 100 at B. So there will be a sudden drop in the value of shear force. And this varies, this is 60 actually. Okay, minus 60 and plus 40. Total is 100. Okay. And from 60 it varies to 0 between B and C. Okay, and at C it is 0, at E it is 0. So shear force between E and C is 0. Okay, yeah. This is how the shear force diagram is. And coming to the bending moment diagram, at A it is 0, at D it is 0. Bending moment at D is 0. Okay, bending moment at D is 0 and bending moment at E is minus 60. Bending moment at D is 0 and bending moment at E it is minus 60. Okay, and at A bending moment is 0. Okay, and at E it is plus 30, and between E and C bending moment at E is 30 and bending moment at C is also 30. Okay, yeah, it is positive bending moment here. Between A and E 30 and between E and C it is 30. Positive. And now the shear force between C and B varies plus 30 to minus 60. So bending moment at B is minus 60 and bending moment at C is plus 30. Okay, so and this is parabolic. Parabolic variation. So you need to find where the bending moment becomes 0 actually. Okay, you need to find the location where this bending moment is 0. For that you need to solve the quadratic equation by equating this to 0. Okay, by equating this to 0 you will get the location of point where the bending moment changes sign, okay, positive to negative, which is also called as point of contraflexion. Point of contraflexion. So meanwhile, let us find the bending moment at x equal to 3 meters. Okay, that means at the midpoint of B and C. Okay, because x is taken from D, so the midpoint of B and C will be at a distance of 3 meters. So substituting bending x equal to 3, you will get bending moment at 3 meters distance. In this equation, we substitute x equal to 3. So putting x equal to 3, you will have 100 into 3 minus 1.5, that is 150, minus 40 into 1.5, that is 60. Okay, 60 minus 10 into 1.5 square. 10 into 1.5 square, that is 2.25, that is 22.5. So you will get the bending moment as 70 point, no, 150 minus 82.5, that is 67.5. You will get 67.5. It is positive. Okay. So at x equal to 3 meters, it is 67.5. So bending moment varies something like this. Okay. Here at 3 meters, it is 67.5 plus. Okay. And this point, the location of this point, which is called point of contraflexion. This point is obtained location by equating bending moment to 0. Okay. And this point F is called point of contraflexion. Point of contraflexion. Okay. Is this clear? So this is how the bending moment diagram will be for the given overhanging beam. Okay. Yeah. Let us take one more example. Draw the shear force and bending moment diagrams for the given overhanging beam. Okay. It is also similar. One side overhanging. Okay. So here we find the reactions. This is how the shear force diagram will be, and bending moment diagram. Okay. Yeah. For the given beam, we find the reactions first by applying conditions sigma ma equal to 0. You will have Re into distance from A, 8 meters. Re into 8 is equal to moments due to applied loads, which are all clockwise. Okay, so they are all taken on the right hand side. So due to point loads first, the moment is 20 into 2 plus 20 into 5 plus 10 into 7 plus 40 into 10. 40 into 10. And due to UDL, first UDL between A and B, 10 into 2 into 1 plus second UDL between C and E, and the intensity is somehow the intensity is this intensity is missing here. It is, I think, from this diagram It is varying 57, so it is 20. Yeah, this intensity is 20 kilonewton per meter. Okay, 20 into 3 into distance of centroid from A, centroid of UDL from A. Okay, that is 5 plus 1.5, 6.5. Okay, yeah, this gives the reaction RE. So the total value here 40 plus 100, 140 plus 70, 210 plus 400, 610 plus 20, 630, 630 plus 390, 630 plus 390. It will be 1020 by 8. So it gives 1, 1, 2, 16 and 7.5 kilonewtons. 127.5 kilonewtons. Okay, RE is 127. And therefore RA is obtained by subtracting RE from the total downward load, okay, which is 20 plus 20, 40 plus 20, 60, 70, 110, okay, plus 60, 170 minus 127.5. So it is 42.5 kilonewtons. 42.5 kilonewtons RE. So after this, we consider various sections between. How many sections we need to consider here? 5 sections we need to consider, because for every change of load we have to consider. Okay, between AB we take one section, BC one section, CD one section, DE one section, and EF one section. Total 5 sections we have to consider. Okay, yeah. For these sections, first 2 sections we consider origin from left. For the rest, you can take origin from right. For the remaining these sections, you can take origin from right. Okay. Yeah. So considering section 1, the shear force at A is shear force at X is RA minus 10 into X. Okay. Left side upwards is positive and downwards is negative. So RA, what is RA here? 42.5. This is shear force at X. Okay. Between portion A, B. And X varies from 0 to 2. The limits for X for 0 to 2. Okay. Minus 10 into X. 10 into X. Okay. So here shear force is dependent of X, position of section. Okay. So at X0, shear force at A will be 42.5. And at X equal to 2, shear force at B will be 22.5. 42.5 minus 10 into 2. Okay. That is minus 20. 42.5. Units are kilonewtons. Okay. Next, bending moment at X is 42.5 into x minus 10 into x into x by 2. Okay. So that is 5x square. Okay. 5x square. 42.5 x minus 5x square. And it varies parabolically if you observe. And shear force at A, shear force at A is 0, putting x 0, sorry, bending moment at A. At x equal to 0, bending moment at A is 0, and at x equal to 2, bending moment at B is 42.5 into 2 minus 5 into 4, that is 20. 85 minus 20, 65 kilonewton meters. You can see 65 kilonewton meters. Okay. Now we take section between BC. Section between BC. So for this, the shear force at section X is RA, that is 42.5 minus 20 minus 10 into 2 minus 20. Okay. So it is 2.5. If you observe this, and the limits for x are from 2 to the limits for x are from 2 to 5. Between BC, the limits are from 2 to 5 for x. Okay. And also it is clear that shear force remains constant because there is no load between B and C. So 42.5 minus 10 into 2 minus 20, that is 2.5. Therefore, the shear force at B and shear force at C is 2.5 constant. And bending moment at X is 42.5 into x minus 20 into x minus 3, x minus 2 minus, this is due to point load, and due to UDL 10 into 2 into x minus 1, 10 into 2 into x minus 1. So that is total UDL is 20 into its distance from section x minus 1. Okay. Yeah. So here the bending moment between B and C varies linearly. Okay. Because there is no load here. So it varies linearly. Understand? So at x equal to 2, we will get bending moment at B as 2 means this term becomes 0, and you will have 85 minus 20, that is 65. It is already seen here. Bending moment at B is 65. And at x equal to 5, bending moment at C is 42.5 into 5 minus 20 into 5 minus 2, 3, that is 60, and 20 into 5 minus 1, 4, that is 80, to minus 140. 42.5 into 5, that is 220, 212.5 minus 140. So it becomes 72.5 kilonewton meters. 212.5 minus 140. Okay, 72.5 kilonewton meters. That is the bending moment at C. Next, coming to portion EF. Right hand side we will consider now. Portion EF, if you consider, the shear force remains constant plus 40, and bending moment varies from 0 at F to 40 into 2 at E. Okay, that is 80 minus 80, negative bending moment. You can observe that it is clear. Okay, so considering portion E, F, the limits are from 0 to 2 because we are taking origin from right hand side. F from F. Okay, so it is 0 to 2. So shear force at X is plus 40. Therefore, shear force at E, shear force at F are 40 constant. And bending moment at X is minus 40x. Okay, and here at x0 bending moment is 0 at F, and at x equal to 2 bending moment at E is minus 40 into 2, that is minus 80 kilonewton. Okay, now you consider the portion DE. X varies from 2 to 3. X varies from 2 to 3. For the section between DE, the limits for X are from 2 to 3. Now, shear force at X is 40 plus 10 into X minus 2, 20 into X minus 2. Sorry. UDL is 20 kilonewton per meter minus RE. Okay. So plus 20 into X minus 2 minus RE. RE is 120. What is RE? 127.5. RE is 127.5. So this becomes 20 into X minus 2 minus 87.5. Okay. Now we substitute the values 2 and 3 for X to find shear force at E. Shear force at E, that is at X equal to 2. It is 0 and it is minus 87.5, and shear force at D is, substituting X equal to 3. X equal to 3. So 20 minus 87.5. So minus 67.5 kilonewtons. And coming to bending moment at X. So RE 127.5 into X minus 2. X minus 2. This is positive bending moment due to reaction. Minus 40 into X minus 40 into X minus 20 into X minus 2 square by 2. That is 10 into this 10. Yeah. Now substituting X equal to 2, you will get bending moment at E, that is at X equal to 2. Bending moment at E is 40 into 2, and that is minus 80 kilonewton meters. And at X equal to 3, bending moment at D is, substituting X equal to 3 here, 127.5 minus 120 minus 10 minus 130 it is. So 127.5 minus 130, it is minus 2.5 kilonewton meters. Okay. So bending moment at D is minus 2.5 kilonewton per. Consider the last section between C and D. Between C and D. Considering right hand side again, the limits for x will be from 3 to 5. 3 to 5. Okay. The limits for x will be 3 to 5. Now, what is the shear force at x? Considering right hand side, shear force at x is, take downward force as positive, 40 plus 10, 50 plus 20 into x minus 2. Okay. 40 plus 10, that is 50, plus 20 into x minus 2, minus 127.5 RE. Okay. So it will be 20 into x minus 2 minus 77.5. Okay. Yes. Now, shear force at D at x equal to 3 is 20 minus 57.5. 20 minus 77.5. And shear force at C is at x equal to 5. So it becomes 60 minus 77.5. So minus 17.5. Okay. Minus 17.5. Next, bending moment at x is Re into x minus 2. That is 127.5 into x minus 2 minus 40 into x minus 40 into x. Okay. Minus 10 into x minus 3. 10 into x minus 3 minus 20 into x minus 2 square by 2. Okay. Yeah, here bending moment at D, it is at x equal to 3. This term becomes 0. Okay. So we'll have 40 into 3, 120, 127.5. So minus 2.5 we'll have. Already we have seen. Okay. Minus 2.5. And at x equal to 5, bending moment at C is 127.5 into 5 minus 2, that is 3. So it becomes 360 plus 22.5, 382.5 minus 40 into 5, 200 minus 10 into 2, 20 minus 10 into 9, 90. So this becomes 310. So it is 72.5 kilonewton meters. Already we have seen this. Bending moment at C as 72.5. Here we have seen bending moment at C is 72.5. Okay. Now these values are plotted as shown here. Okay. So shear force at A is plus 42 and at B it is 22.5. Also there is a drop in value of shear force by 20. to 2.5, 22.5 to 2.5 because of point load, and that remains constant up to 2.5. Okay, and there is again a drop of shear force from 2.5 to minus 17.5, that is by 20 units because of 20 kilonewtons load. Okay, and between C and D there is a drop of shear force by 40 that varies uniformly. Okay, because of UDL 20 into 2, 40. Similarly, there is a sudden drop in shear force by 10 units at D, 57.5 to 67.5 here. And again, there is a uniform drop in the value of shear force by 20 units, 20 into 1 UDL. Okay, yeah, minus 87.5, minus 67.5 to minus 87. Now there will be a rise in the value of shear force to plus 40. That is by 127.5 kilonewtons. Okay, because of reaction. Okay, and that remains constant up to F, and there will be a drop in the value again at F due to point load. Okay, this is how the shear force diagram will be. Similarly, the bending moment diagram. Okay, you can locate this point of inflection by equating bending moment between D and C to 0. Equating bending moment between CD, this bending moment, to 0, this value. Yeah. By equating the bending moment between CD to 0, you will get, because bending moment at D is minus and bending moment at C is plus. So between D and C, the bending moment changes sign. That means it becomes 0 at one point. By equating bending moment equation to 0, you will get X value by solving this quadratic equation. Okay? Yeah. So that's all for now. Let us end the session at this point. Okay?
Like, share and subscribe. Hit the bell icon for more updates.